Section 4.2 of Anton is about subspaces. So suppose we're starting off with a vector space V, which you can think of as just Rn, although there are other types of vector spaces, but all the finite dimensional ones turn out to be exactly like Rn. Okay, now a subset of a vector space, a subset W of our vector space V is called a subspace of V if W itself is a vector space under the addition and scalar multiplication of V. So what does this mean? All right, so we've got our vector space V, and W is some part of it, some part of our vector space V. So in terms of a picture, I've got maybe W is this thing here, and because elements of W are also elements of V, we can define addition of two elements of W as their addition considered as elements of V, and then take a real number, multiply an element of W by the rule that comes from the fact that V is a vector space. Okay, and so roughly a subspace is something that's a part of a vector space in such a way that that subset itself is a vector space. So a small, simple theorem is that if W is a set of one or more vectors in a vector space, then W is a subspace of V, if and only if the following conditions are satisfied. That if you have two vectors in W, their sum is in W. So remember, this sum is part of the data of how to add in the vector space V. Okay, secondly, if you've got a real number, in other words a scalar, and a vector in W, then that scalar multiplication, K times U, also lands inside W. It will definitely land inside V. That's part of the definition of V being a vector space, but we require that it also land inside W. So here are some examples and non-examples. So in R2, that's our vector space V. Let's take the subset being a line through the origin. Any line. Here I've chosen one that passes through 2, 1, given by the equation y equals 1/2 x, for example. And any such line will, again, as long as it passes through the origin, will form a subspace of R2, because you take any point in here, adding it to another point in here will land you back on that line, and then take any point in here and multiplying it by a scalar will, for example, if I take the point 2, 1 and multiply it by the scalar 2, I'll land at 4, 2, and I'll land back on the line for any vector, any scalar. So this line is an example of a subspace of R2. And specifically, W is a subspace of points where, here's just another way of writing it, the x-coordinate is anything, and the y-coordinate is x over 2. For example, if x is 2, y is 2 over 2, or just 1. Okay, let's give an example of something that's not a subspace. Well, any line that's not through the origin is not going to be a subspace, because a subspace has to contain 0, 0. Because one of the requirements of a vector space is that it contains the 0 vector, and it turns out that there's only going to be a unique 0 vector. So in R2, that 0 vector is 0, 0, and so in any subspace of R2 has to contain 0, 0, because any vector space has to contain the 0 vector, and a subspace is by definition a vector space. The example of a subset that's not a subspace. So we look at the parabola as a subset of R2, and this is not a subspace, it's a subset, but not a subspace. Again, subspace is referring to the vector space structure, in other words, the addition and scalar multiplication. And so this parabola is a set of points, or set of ordered pairs, whose y-coordinate is the square of its x-coordinate. And there are many reasons why this is not a subspace. But one, for example, is that, well, we know 1, 1 is in W, it's at this point here, and then W has to be what's called closed under scalar multiplication. In other words, if I take a scalar like -1 and multiply it by take it and multiply a given element of W, I have to land back inside W, but I don't. For example, -1, 1 which is the result of taking the scalar -1 and multiplying this vector 1, 1, I don't land inside W, and so W is not a subspace. Here's an example that considers these somewhat strange function spaces that we talked about in the previous video. So f for function from -infinity to infinity, this is the set of functions that have -infinity to infinity, this interval, the real entire real line, as the domain. And let Pn be the set of polynomials of degree less than or equal to n. And so what is Pn? It's functions f of x of this particular form. These are what are called polynomials. So the numbers a0, a1 up to n, those are real numbers. And the x is our variable. And so this here is a function on -infinity to infinity. Because if you give me a number in -infinity to infinity, like 1, I can plug it in for x and I get an output. And so f of f here, this polynomial is a function. So P of n is a subset of this function space. And in fact, I'm claiming that it's a subspace. Why? Because if you add two polynomials of degree n or less, you'll end up with a polynomial of degree n or less. And if you take a scalar, like a real number, and multiply through by that scalar, multiply a polynomial through by that scalar, all those coefficients, the AIs, will get multiplied by that scalar, and you'll end up with a polynomial of degree n or less. Don't worry too much about this example. It won't come up in this particular course too often. The case of Rn is much better, and its subspaces is what we'll focus on. Okay, here's a definition we've seen before in the context of R vectors in Rn. So we say that we're trying to define this term linear combination. So let W be a vector in some vector space V. For example, V could equal Rn. And then we're saying that W is a linear combination of some other vectors, or possibly involving W. But anyway, some vectors V1 up to Vr that are in our vector space V. If W can be expressed as W is equal to the scalar k1 times V1 plus scalar k2 times vector v2 plus the scalar kr times the vector vr, where these are scalars and that are called the coefficients. So it's a linear combination. W is a linear combination of v1, v2, all the way up to vr. Here's an example that we've seen before. So take W to be this vector 3, 4 in R2 and express it as a linear combination of these two vectors, 1, 0 and 1, 1. Okay, so, well, we might not have seen this example before. We've seen the example where this vector here is the standard basis vector, but in this case, this is not the standard basis vector. Okay, but nevertheless, so what we want to express, we want to express this vector 3, 4 as a linear combination. In other words, some coefficients or constants or scalars k1 and k2 we have to find, so that 3, 4 equals k1 times 1, 0 plus k2 times 1, 1. And now k1 times 1, 0, this is scalar multiplication, so we multiply each component by k1. That turns into k1 times 1 is k1, k1 times 0 is 0, k2 times 1 and 1 are k2 and k2. Now we have to add these two vectors. Vector addition is done component-wise, so k1 plus k2 is this first component, 0 and k2 is the second component. And so this vector has to equal the vector on the left-hand side. Two vectors are equal if and only if their respective components are equal. And so 3 has to equal k1 plus k2, and 4 has to equal k2. So we have to find these numbers k1 and k2 that satisfy this condition. So this is a quite simple system of linear equations. We don't have to do any reduced row echelon form or throw this into a matrix or sage. We can just solve it by inspection. If k2 is 4, well, solving this equation for k1 gives k1 is equal to 3 minus k2, and k2 is 4, so this is equal to -1. So we found our two scalars, k1 and k2, 3, 4, as this linear combination -1, times 1, 0 plus 4 times 1, 1. And this is our answer. Let me end this video with one more definition, and this is the definition of a span. So we say that vectors v1 up to vr span a vector space V if every vector in V is some linear combination of these vectors v1 up to vr. A specific example is that Rn is spanned by the standard basis vector. Every vector in Rn is a linear combination of the standard basis vectors.